Good afternoon, bon après-midi. Welcome to the penultimate edition of the Physical Society Colloquium for the academic year 2020-2021. I'm coming to you live from the brutalist majesty of the Rutherford Physics Building at McGill University in beautiful downtown Montreal, where chalk can be even more elusive when you really need it than a certain notable Sicilian theoretical physicist. If you are in the Zoom session and you prefer not to be recorded or live streamed, please log out of Zoom and join us via YouTube. This afternoon, we will have a 45-minute talk followed by 15 minutes of questions and answers. To ask a question in Zoom, please use the raise hand feature following the talk. To ask a question in YouTube, please enter it into the chat. The questions will be relayed to me by my sidekick following the talk. If you would like to ask a clarifying question in the Zoom session, please type it into the Zoom chat and I will try to raise it with the speaker during the talk. After the Q&A session at the end of the talk, the live stream and recording will stop. Professors will be asked to log out of the Zoom session, and undergrads, grads, and postdocs, as well as other non-faculty in the Zoom session, will be invited to the après colloque, a chance to get to know the speaker in a more intimate setting. With that, I will now pass to Professor Michael Hilke, who will introduce the speaker. Michael.
Hi, so it's with great pleasure that I introduce to you Mike Manfra, kind of in a very subjective bio, but basically, Mike, I think, studied at Harvard and then Boston University, and then before being a postdoc at Bell Labs, where he was working with Lorne Pfeiffer, and that's essentially why I met him the first time. And for those who are not in the field, Lorne Pfeiffer was the guy who made like the best two-dimensional electron systems in gallium arsenide, definitely back then. And so I guess Mike had the opportunity to learn from the very best sample makers in the world and making sort of the highest mobilities. And I think when I met him sort of there, and like many people at that time, we're trying to get like the good samples from Lorne Pfeiffer, and Mike was also always there, and I think he was mostly working on gallium nitride back then. But I think since he has also worked on many other sort of growths of other samples such as gallium arsenide and indium antimony and I guess indium arsenic and superconductivity and so on. So he has spent, I think, about roughly 10 years at Bell Labs before moving to Purdue University, where he set up this very impressive lab, which not only contained one MBE, but actually 3 MBEs. One, I think, which focuses on gallium arsenide, the one is gallium nitride, and then the third one, which is sort of mixing superconductivity with other materials. And in addition to that, not only he does this sort of world-class MBEs, but he also makes low temperature measurements. And I'm not sure, actually, I prefer not to ask who does now like the best samples. Is it, Pfeiffer or Manfra? It's I will not get into that competition, friendly competition. But what I would like to point out is that, maybe the most important thing that he made this very interesting discovery recently on this anion braiding. And then that's, I think, what he will focus his talk about today. And it's really something people have been fantasizing for a long time. And I think these are really amazing, interesting results which came out recently, which I very much look forward to hearing more about from Mike. And so it's really a pleasure to introduce, to welcome him at McGill, and at least virtually. And please, Michael, Mike, it's all yours. Thanks.
Well, thank you, Michael, and thank Bill for this kind invitation to speak at McGill. It's a great opportunity. I really appreciate it, and so thank you. And yes, I'm going to try to tell you today about our observation of anionic braiding statistics. That's sort of an imposing title. I'll try to be as pedagogical as I can and give you some background of what the heck I'm talking about. As we go, I know this is a colloquium, and in addition to many experts in the field who are at McGill, there are a variety of students and postdocs and others. So I'll try to explain some of the basics so that we sort of get the point of what the system is we're trying to look at and the physics we're after. And of course, if there's anything I say that is unclear or just doesn't make any sense, please interrupt me and I'll try to clarify it. I do want to point out that these experiments were performed by just an outstanding researcher, James Nakamura, a postdoc in my laboratory, and the samples were also grown in my laboratory, but by other very talented researchers as well, Shuang Liang and Jeff Gardner. Okay, so let's plow ahead. Oops. Don't seem to be able to advance now.
Try clicking on your screen. It's probably lost focus.
Click on my screen. Okay. Oh, there we go. Great. Thank you. So the topics I'm going to try to cover today are, I'm going to tell you about anyons and the fractional quantum Hall effect. And of course, I will eventually tell you what an anyon is. I'm going to tell you about the Aharonov-Bohm effect and what braiding statistics are and how we probe these in the electronic analog of a Fabry-Perot interferometer. And I'll also tell you about some of the challenges of operating electronic Fabry-Perot interferometers in the quantum Hall regime. And this has been problematic for quite some time and has frankly limited the field's ability to make the types of measurements that we are all as a community interested in. And I guess our innovation was a new heterostructure and device design that really allowed us to see some of the physics that it was always there, but just hard to see. So I'll tell you about the operation of our interferometer, both in the integer quantum Hall regime, where nu=1 is the prime example, and then in the fractional quantum Hall regime at filling factor 1/3. And again, I will define these things for everyone. So, and then I'll show you the evidence for anyonic braiding statistics, and as we do more and more experiments, some of the data that's building up to substantiate these claims. Okay, so this might not be known to everyone, but in 2020, anyons were revealed in experiments, and there were two experiments, one by a group in Paris where they were able to access fractional statistics associated with anyons, building a very beautiful, what's called an anion collider in a two-dimensional electron gas. And this, without question, exposed the fractional statistics at the nu=1/3 state. But one thing was about this experiment is that it inferred the fractional statistics from looking at noise correlations of partition currents at a what's called the QPC. And they're very beautiful experiments, a great accomplishment, but it's a little hard to see directly the fractional nature of the particles through this type of work. We followed up, their result was first, but we followed up with what we think is a direct observation of anyonic braiding statistics. And if you're after statistics and phase, this is all about measuring a phase. One way to do it is to look using interferometry, and it sort of clearly brings out the presence of the phase that's developing as the quasiparticles move around the interferometer. And so these two experiments together, I think, really gave the field confidence that we were, as a community, observing the fractional statistics in the system, in which the prediction of fractional statistics or anyons is over 40 years old, but the direct confirmation is taking quite some time, and because the development of the materials and experimental probes has been the challenge. So this is the topic that I'll try to explain to you as best I can. And before we delve into any real experimental details, everyone in the audience may be saying, okay, great, what's an anyon? What does it have to do with anything? And this is really a question of quantum statistics in reduced dimensional systems. And if we compare what happens and what's possible with quantum statistics in 2 versus 3 dimensions. And so what do I mean by quantum statistics? I'm trying to ask the question, what happens to a many particle wave function under exchange of identical particles? Or if I use a term, braiding identical particles, wrapping one around the other, what actually happens to that many particle wave function? In our basic quantum mechanics class, of course, we learned that, at least in 3 dimensions, there's only 2 types of particles, bosons and fermions, that have to do with the symmetry of the wave function under particle exchange. So we know for bosons, if I have a multi-particle wave function, I exchange 2 of those particles, I get the same wave function back under that symmetry operation. So if you want to think of it in terms of phase, the exchange generates a phase factor of 2 pi. Of course, the only other allowed symmetry that we know of is the symmetry of fermions, where we actually exchange two particles and the wave function again is the same, but it's multiplied by a factor of -1. So it's the same wave function multiplied by -1, or if you want to think of it in terms of a phase factor of pi. And again, this fundamental symmetry boils down to the fact that if we exchange these particles twice, do exchanges of two particles once and then do it again, and the wave function is single valued, it has to come back to the value it had before we did anything. So this process is essentially equivalent to an identity operator, and so the only way we can do this is have the particular symmetry of plus or -1 for multiplying the wave function when you do this single exchange. But in two dimensions, and the reason that's true comes down to this realization that if you try to take particles around each other and do, or excuse me, if you exchange particles twice, it's equivalent topologically to taking one of the quasiparticles and wrapping, one of the particles and wrapping it around the other, bringing it back to its original position. And of course, that is the same as doing nothing, bringing the system back to its original state. And so this is essentially an identity operator. And so these are the allowed symmetries. In two dimensions, things are different though. There's a well-defined meaning to winding a particle around another or braiding one around the other particle. And you can't reduce that to an identity operator for these exchanges, because then you'd have to cut across, it's called cut through the particle, or the first particle that you wrapped around in the process of trying to bring the first one back to its original position. And that means that these winding operations or braids actually have a well-defined meaning. And that has very important implications, as of course does the symmetry of bosons and fermions. We know that we get vastly different behavior for multi-particle systems, whether they're bosons or fermions. But in 2D, this is even can have even more drastic implications. We can have fractional statistics, and what that means is instead of having just pi or 2 pi, we can have a multiple of 2 pi, where we have something that's called an abelian anion that develops a phase factor of I 2 pi times alpha, where alpha is called the fractional or anyonic angle. And this can happen in low-dimensional systems, highly interacting systems like the nu equals 1/3 fractional quantum Hall state that I'll describe to you later. But even more exotic statistics are potentially accessible in 2 dimensions. Not only can the system develop an arbitrary phase under particle exchange, or meaning a fractional phase, but there's also possibility for non-abelian statistics as well. And for some highly correlated states, exotic states, including the 5-Haas fractional quantum Hall effect, or 2 topologic superconductors that we also look at. The braiding corresponds not to a rotation and just a development of a phase factor, but it's actually a unitary rotation within a degenerate manifold of states. And so actually the particle exchange brings you into a different configuration than you started out with. And that has a host of implications. And it's one of them being that you could use this property for storing quantum information and manipulating quantum information. So that's a lot of the drive for looking for non-abelian states and exposing these types of behavior, that they could be used for process of quantum information storage and manipulation, but done so in a way that's protected against decoherence, because this corresponds to a topological process where you have to exchange the position of particles or braiding around each other, that it would be less sensitive to decohering effects that and local perturbations that we know are plaguing our other formats for qubits. And so that's sort of the background. And all this comes down to, again, why is this possible? Because the world lines in 2D can form knots, while in 3D exchanges can be deformed into identity operators. And this was identified quite some time ago in theoretical work. And this term anion was actually generated by Frank Wilczek back in the early 80s for just a quip for saying anything goes. So, all right. So how do we actually realize this type of behavior in a physical system? Well, one way is we generate a two-dimensional electronic system at the interface of semiconductors with different band gaps. And so the system I work on, I'm going to describe, is just a layered semiconductor where we have a narrow band gap material, gallium arsenide, that is grown, and then within the MBE chamber with an atomically flat interface in monolayer resolution, we grow a wider band gap material on top of that. That wider band gap material forms a barrier for electrons in keeping them from moving in the vertical direction. And if we apply, or excuse me, supply silicon atoms, which can donate electrons, they're a donor in 3-5 systems, we can have excess electrons that get trapped at the interface, this boundary, as I show you on the right-hand side. What's basically a band diagram. The red trace shows the potential, if you want to think about the potential that the electron sees as a function of position along the vertical direction. And the blue trace basically is a map of the electronic distribution near the interface. And so we essentially develop a two-dimensional electron system right at the interface of two dissimilar semiconductors. And these electrons are confined to move in they can't move in the Z direction. They're basically stuck there at this interface. So in essence, they become two-dimensional, but they are free to move in the XY plane, or parallel to this interface. And so that's what we call an effective two-dimensional electron system. Now, interesting things happen. That's sort of I represented in the leftmost panel by this cartoon of a flat sheet with the blue spheres representing the electrons when we turn on a magnetic field. And there's very interesting physics that's generated when you take this combination of two-dimensionality and large magnetic field, and that's what I'll describe now. So again, I recognize that there are certainly numerous experts in the audience, but there are also probably people who are not so familiar with the quantum Hall effect. So I'll try to give you the most basic of introductions so that we at least all can speak the same language. So if we take this two-dimensional sheet of electrons and apply a perpendicular magnetic field, as shown here in this figure, the magnetic field can be represented by the vector potential, of course, or the gradient, the cross product of the gradient and the vector potential. Oops, I went the wrong way. Okay. Now, what does the Hamiltonian for this system look like? Well, of course, there's a kinetic energy term. And so the momentum gets replaced or augmented by the vector potential in a magnetic field. So there's a term that represents essentially the kinetic energy in a magnetic field. Now, these are all real physical systems. So there's disorder in the system. There's inevitable disorder. We try as MBE growers to minimize it to the extent possible, but there's always imperfections and sources of scattering. So we have to include a disorder potential as well. Now, interestingly, there's also the mutual interaction of those electrons confined in a plane, and they're all in close proximity, and they interact strongly, or they can interact strongly with each other. And this gives rise to a whole host of effects in interesting physics. So the electron-electron interaction is not necessary for the integer quantum Hall effect, which I'll sketch out for you right now, but it's essential to the fractional quantum Hall effect. It's at its origin. And that these interactions are what drives the interesting physics. But let's first start with the simplest problem we possibly can, and this is something we all solve in our beginning quantum mechanics class: non-interacting electrons in perpendicular magnetic field. And so then the Hamiltonian reduces just to H naught here, where we have a free electron in 2D in a magnetic field. And we know semi-classically and qualitatively what's going to happen as we turn on this magnetic field. The electrons will start executing little cyclotron orbits, if you want to think of it classically, going around a little circle as we increase the magnetic field. And the cyclotron frequency, which will be represent the energy spacing of the quantum mechanical levels that we arrive at in a minute, is basically linearly proportional to the magnetic field and inversely proportional to the mass of the carriers. But you know, semi-classically, you think of these things as undergoing little circular orbits. But actually, this is a problem we can solve analytically with single particle quantum mechanics. And I won't write out the eigenstates. It depends on the gauge you choose, but nevertheless, it can be solved analytically. And those eigenstates are represented by 2 quantum numbers and a principal quantum number, and K, another quantum number that's related to momentum. And the eigenenergies, as I alluded to a moment ago, are excuse me, my phone's going in the background, so there's a problem here. The eigenenergies, though, are given by h bar omega c, or h bar times n plus 1/2, where n is an integer. So this h bar omega c is just Planck's constant times the cyclotron frequency. But the important point here is to notice that the eigenenergies are specified by 1 quantum number, this principal quantum number n, while the eigenstates are labeled by 2 quantum numbers. And so this principal quantum number we call the Landau level number, after Lev Landau, who solved this problem back in the early 30s, and is associated with orbital quantization. But it also implies that there's going to be a large degeneracy, right? We have these eigenstates that have multiple quantum numbers, quantum numbers, but the eigenenergies depend only on the principal quantum number. So we're going to have a large positional degeneracy, which scales linearly as the magnetic field and times the area that's covered by the 2D gas. And that's so it scales linearly with magnetic field, so the degeneracy goes up and up. The phi naught here is a magnetic flux quantum, just so you'll see that often during the talk. So just so you know, that's h over e is the magnetic flux quantum. So if we were to look at the density of states, I'll first look at the lower right-hand panel here, and before defining this quantity called nu. The density of states, as we turn up and crank up the magnetic field, will break up into these discrete called Landau levels, separated by h bar omega c. And as I said, they're highly degenerate, the degeneracy increasing as we increase the magnetic field, as does, of course, the separation between the levels. So if you looked at these levels, you can imagine that there'd be times when we fill these Landau levels with electrons and there'll be a gap in the spectrum, and times when the Landau levels are partially filled and then we won't have a gap in the spectrum. So in order to keep track of this, we define a quantity called nu, which is basically the ratio of the density of electrons to the magnetic field times the magnetic flux quantum. And it tells us the number of Landau levels filled with electrons, and we call it the filling fraction or the filling factor. And as I mentioned, there could be times when the ratio of the density of electrons to the magnetic field is such that we have an integral number of these Landau levels filled. So you imagine this low, if I had exactly 1 electron for every orbital allowed, then I'd be at filling factor nu equals 1. And I'd have this lowest Landau level filled. My chemical potential would be in the gap between the lowest Landau level and the next Landau level. And you can imagine that some interesting things might happen in that particular case, where you have a completely filled Landau level and your system is in the gap, or your chemical potential is in the gap. Now, it could be that I have 2 Landau levels filled. I have twice as many electrons as I have for states allowed, and then I'm at filling factor nu equals 2. And then my chemical potential would be between the second Landau level and the next highest Landau level. And the features that we see in transport when we measure these samples is highly dependent on this filling factor, and the physics of the quantum, or the integer quantum Hall effect, is associated with having integral filling, an integral number of these Landau levels filled. And that's what I'll show you in a moment. Of course, it's also completely possible that we have a fractional. We haven't completely filled 1 Landau level, and our chemical potential is actually within a Landau level, meaning there's available states in that Landau level. There's more states available than we have electrons, and you might expect the physics or the transport properties to be quite different. And that's what I'll try to show you now. So again, in a try to simplify picture, a fully filled Landau level corresponds to the having nu equals 1, nu equals 2, and that corresponds to the physics of the integer quantum Hall effect. So what does that mean? Well, if I have all the states in the center of the sample, or what we call the bulk of the sample, filled, they carry no net current. The bulk is insulating. So if I attach a source and a drain contact to the sample and force a current through it, what we actually find is that all the current is carried by chiral edge states, the little red states, if you will, the skipping orbits that you see, that the half circles that go along the periphery of the sample. And these edge modes are gapless in that we see the current is actually carried by these modes that propagate along the edge, but they're also topologically protected. There's no backscattering in these. And so actually, while the bulk is insulating, the current carried along the edge occurs without any scattering. And so if you look at how the current flows in the sample, it's sort of along this red path here, it flows without dissipation along the edge. So there's, if you measure the voltage drop that occurs, you'd actually see 0 longitudinal resistance when the filling factor is such that an integral number of Landau levels is filled. This is the physics of the quantum Hall effect, or the integer quantum Hall effect. Concurrently, if we measure the transverse voltage, we find that each Landau level contributes 1 quantum of conductance. So if you measured the transverse conductance, you'd find that the conductance is given by nu times e squared over h. Or if you typically measure the transverse or Hall resistance, you'll see that it's given in units of 1 over nu times h over e squared. And so this is the transport that I'll show you an actual trace in a second. Of course, this is just a cartoon, but when we have the integral number of Landau levels filled, we expect to be in a state without dissipation, where we see current flowing without resistance along the length of the sample, and the Hall resistance of voltage across the sample to be quantized in units of this quantum of conductance. So now, sorry to go back, this is all a single particle effect. I haven't talked anything about interactions yet, and can be explained with relatively simple single particle quantum mechanics. Now, the extension of that, you say, well, okay, if I have just a fraction of a Landau level filled where my chemical potential is not in a gap, say, for example, I crank up the magnetic field such that I have 3 times as many states available as I do electrons, I'd be at the nu equals what we call 1/3 state. But then you'd say, well, the chemical potential is not in a gap, maybe, or I shouldn't expect to see anything very unusual happening here. There's a huge degeneracy, and I expect the state to be very compressible. What I mean by compressible is that there's no gap in the density of states. But that reasoning only goes so far, and it's because I've only considered the kinetic energy in a magnetic field. I haven't considered the mutual electron-electron interactions. And if you think about it, if I'm in the lowest, if I crank up the magnetic field, all these guys, electrons, are in one kinetic energy state. They're all degenerate, and there's a huge gap to the next lowest lying kinetic energy state. Then all that's left to determine the physics is the mutual interactions and disorder, which I'm still ignoring. But the mutual interactions are actually what dictates what's happening in this case, and we can kind of throw out the kinetic energy. In that case, what we actually find is solved first by Laughlin and seen by Stormer and Suey back in the early 80s, is that there are certain configurations filling where we generate a very complicated wave function, but also that ground state that is separated from excited states by a gap in the spectrum. And these are the fractional quantum Hall states. And again, this physics is completely determined by the mutual interactions of the electrons. And so there are very special filling, rational fractional fillings in which we will see the same phenomenology of the integer states, but it's driven by much different physics. So what do we see in transport? We will get an incompressible fractional quantum Hall state. So what does that look like? So here's the actual, I finally got into it after all this time, transport data. This is data from a very typical, nothing special sample from my lab, but you see in the low magnetic field range, say below 4 Tesla, you see the integer filling, nu equals 1, where there's a quantized Hall plateau, 0 longitudinal resistance, n equals 2, n equals 3. But then as I crank up the magnetic field and increase the degeneracy of the states, you see the same phenomenology of flat plateaus in the Hall resistance and zeros of resistance in the longitudinal trace occurring at certain rational fractional values of filling. And this is the area that is most interesting because sort of the implications of having this type of transport where you see a gap in the spectrum has certain implications. And the implications are the excitations of the fractional quantum Hall states are actually emergent quasiparticles. And what do I mean by that? Well, they're collective states. They have well-defined quantum numbers associated with them. We call them quasiparticles, but they don't exist on their own. They're emergent within this highly interacting system. And they have really strange properties. the quasiparticles, say we look at the one at 12 Tesla, the nu equals 1/3 state, carry fractional charge. Actually, the quasiparticle, if you will, splits up. It has a unit of charge associated, which is only 1/3 of the bare electron charge. And this was first predicted by Bob Laughlin back in '83, but it actually took quite some time for verification of this through shot noise experiments that I want to explain to you, that there indeed actually is fractional charge in the fractional quantum Hall regime. Another implication is that these quasiparticles are not only fractionally charged, they carry fractional braiding statistics. This, if you will, for these primary Laughlin states, it's the Berry phase that builds up, or the Berry phase or the Anyonic phase for a given state is given by 2 pi, the effective charge over the bare electronic charge. And so what does that mean? In this little cartoon here, I have these quasiparticles that I wrap around each other, and the phase that's developed in the quantum mechanical wave function for this multiparticle state is actually 2 pi E star over 3. So if I were at nu equals 1/3, for example, that means I develop an anyonic phase of 2 pi over 3. And this again was a theoretical prediction that happened right or within a year of Laughlin's description of the fractional quantum Hall state. And Bert Halperin, Avro, Schrieffer, and Wilczek were quick to recognize this, and Steve Gilson also had important contributions to this field, Jean or Jane, a lot of people, a lot of theorists did. That an implication is that these quasiparticles have fractional statistics, and of course that's very strange, right? As I told you earlier, the things we actually know about as fundamental particles are either bosons or fermions. Now, again, you see the date associated with these theoretical the descriptions of the state and the implied fractional statistics. And I just told you at the very beginning, 2020 was the year we could more or less say that we've actually observed these. So what's the problem? Why did it take so long to try to expose these properties directly? And it actually turns out to be, for me at least, very interesting interplay of device design, materials design, and some pretty basic physics. And I'll try to explain to you in the last 15 minutes or so. I may go over. I hope no one's going to turn me off, but certainly I'll try to move more quickly now. Okay, so as I said, this is a statistical phase that's built up as we, and I showed you this little cartoon of one quasiparticle going around another, and we're interested in phase. So as you might expect, if you're trying to expose phase, one way of looking at this is to do an interference experiment. And so what we're going to build is the analog of the Fabry-Perot interferometer that's used in optics that you're maybe familiar with. And we're going to try to operate this thing in the quantum Hall regime. And that's going to be the source of sort of the problems and the sort of design changes that we had to make in order to get this thing work. But what does this really mean? So you have this blue area, which you can just take to be the two-dimensional electron gas, and I'm going to define these surface gates. And these yellow regions are the surface gates that will be used to locally deplete electrons and define a path for the current to flow, and the source and drain, or where the current starts and where it's going to end up flowing in and out of the device. So I'll put voltages on these gates so that they're locally, the electron path is defined and the electron density is locally depleted under the gates. And as we talked about earlier, in the quantum Hall regime, current is carried by edge states. So these edge states will go along the periphery and come to this constriction. This first constriction I show you of these two yellow gates that come into pretty close contact, that's called a quantum point contact. And what we do is by putting a potential on these gates and bringing the edge state in close proximity to the counter-propagating edge, we can induce partial backscattering. And so this current comes in, there's partial backscattering, so some of the current goes off, and that's controlled by the voltage that we put on this and gets shot back around towards the source contact, sorry. But if we tune things right, most of the current continues to propagate on the interior of the interferometer until it comes to this second point contact, where again we can induce some amount of backscattering. So the current that comes into the second point contact, some of it gets backscattered, a small amount, and continues along the periphery, the interior of the Fabry-Perot interferometer. Most of the current actually just propagates towards the drain contact. But of course, if this is a coherent structure, there's a phase that's built up as this partially backscattered current circulates around the interferometer, and it rejoins with the partially backscattered current from that occurred at the first quantum point contact. And again, if this is phase coherent transport, the backscattered current will depend on the relative phase that's built up along those two paths. So if I wanted to look at what current is actually backscattered, as you might expect, there's a term proportional to the amplitude of backscattering or reflection coefficient squared that occurs at the first QPC. That's fixed by the gate voltage. There's a term that's proportional to the amplitude for backscattering squared at the second QPC, but there's also a cross term, if you will, that depends on this relative phase that's built up. And this current that flows through the interferometer will vary as a function of cosine theta. So what is cosine theta here? This cosine theta is the actual interference phase that describes the interferometer. And it's composed of a couple or has contributions from a couple of different sources. What's called the AB phase, the Aharonov-Bohm phase, is proportional to the product of the area times the magnetic field divided by the magnetic flux quantum. And of course, I can change that phase by either changing the area of the interferometer, which you could think of naively as just changing the gate voltage on one of those big side gates to squish in or pull apart the area of the interferometer. Or I could tune it by cranking up the magnetic field that penetrates through the center of the interferometer. And that way I could see, looking at this term, periodic modulation, as this product AB would, of course, vary as the cosine with a periodicity associated with the magnetic flux quantum. Now, if I'm in the fractional quantum Hall regime, this term actually becomes a little bit more complicated. And this is actually what of most interest to us. This phase that develops will have extra terms. But as I just described, I forgot to advance, but you can measure the interference by measuring electrical conductance across the device. You operate the device by changing the area, either by the side gate voltage or you change the magnetic field. And if you looked at the expectation for the signal that comes across, or basically how much current is transmitted through the device, you expect to see lines of constant phase with negative slope in the BVG plane. So theoretically, if I'm just in the integer regime and I plot out lines of constant phase as a function of magnetic field and side gate voltage, I would expect to see something what's termed a pajama plot colloquially. But basically, these lines with negative slope represent lines of constant phase or constant conductance. And they will oscillate with a periodicity given by essentially the change in the Aharonov-Bohm term, which we can associate with changes in the or periodicity associated with the magnetic flux quantum. And this was worked out in great detail by Bert Halperin and collaborators back in 2011, what we might expect for such an interferometer in the integer quantum Hall regime. But now let's move ahead and say we're going to move beyond the integer effect, but we're interested in looking in the fractional regime. And here's where things get pretty interesting in that this AB phase that I first described actually gets modified. It gets scaled by the effective charge of the quasiparticles, meaning that the periodicity will no longer be phi naught, but phi naught times the effective charge. And that will tell you something about the effective charge of the quasiparticles in the interfering edge. But really, the interesting term is that this interference phase is actually sensitive to the anyonic phase of the quasiparticles. And the phase that develops is sensitive to the number of localized quasiparticles. That's that little vortex that I drew in the center of the interferometer represents one of these quasiparticles. The number of the quasiparticles localized in the interferometer times the anyonic phase contributes to this overall interference phase that we measure. So you could imagine that as a function of parameters, say voltage or magnetic field, that the number of localized quasiparticles has to change discretely. So there'll be phase slips in principle associated with the addition or subtraction of localized quasiparticles. And that will tell us about the anionic phase. It's a direct way of measuring what the anionic phase is in principle. That's what our theorist friends tell us. Actually turns out not to be so easy, and I'll show you why now. So the problem is I've completely neglected the interaction between this small object. I call it an interferometer, but it's actually not that different from something that we term in the field of quantum dot. It's a small microscopic object that has a charging energy associated with it. It takes energy to move charge in and out of this small object. And if you will, you can think of it a self-capacitance. There's a capacitance associated with adding or removing charge. And what that does is actually there's this compressible edge state that I told you about that couples the charge in the interior of the device to the charge at the edge. So while naively I would expect these lines of constant phase propagating with negative slope, what I actually see in reality is in a typical device, you can see in the, say, the integer regime, lines of constant phase developing into a pajama plot, but the slope is completely wrong. They actually go the wrong way. And this is an indication of something called Coulomb-dominated oscillations. Okay, what does that mean? It means that the interaction of the charge into the interior of the interferometer or quantum dot is coupled to the charge at the edge, and the edge is compressible and it can move, meaning the area is not fixed of the device. You think this is a sort of an inert object that has fixed area. That's actually not true when you take into consideration this strong electrostatic interaction. So this bulk edge interaction causes the area to change with magnetic field, which is very strange to think about it. If you think about it, you crank up the magnetic field, you don't do anything intentionally to change the area by changing the gate voltage, but the area actually changes. You can't change A, the area, and B independently. You increase the flux, but increase the magnetic field, but the flux actually decreases. Why? Because the area shrinks. Why? Because it's trying to minimize the overall electrostatic energy. And you say, okay, that's the fact we hadn't considered it. What's the big deal? Well, if you get into the gory details of it, it actually makes braiding in the fractional regime completely unobservable, because any change that's associated with the fractional statistics of bringing in a quasi-particle is compensated for, if you look at it in detail, by this change in area. So it completely obscures the observation of phase associated with abelian anyons in principle. So it's not just it diminishes it, it makes it in principle if you're in this what's called the extreme Coulomb-dominated regime unobservable. So that's a real problem that was understood by the theorists and was seen in many experiments. So how are we going to reduce that? That's really where the new design of experiments comes in. And just to give you a flavor before we move on, there's a spectrum between what we call the Aharonov-Bohm regime, the sort of idealized version of these lines of constant phase with negative slope occurring. And that, of course, occurs in the limit of very weak bulk edge interactions. You have something that's relatively inert. And so I don't worry about those interactions, and that simplistic picture that I gave you before should work. Now, there's a spectrum of what behavior you will see, and that depends on how strong this bulk edge coupling is. So you get to the extreme edge, and panel E that I showed you actually in an experiment, it's called Coulomb dominated. And that's the regime where everything just gets, in terms of Anyonic statistics, gets washed out. And depending on where your device is, you'll see any types of interesting behavior in these conductance plots as a function of magnetic field and gate voltage. So the theorists understood this before we experimentalists did. But and I don't want to go into details because it's so late in the presentation, but it really depends on the ratio of some couplings and basically how strong the bulk edge coupling is compared to what you might call this, the edge stiffness, the energy that it takes to add charge to the edge. But for this purpose of this talk, the real salient point is that you cannot observe the Anyonic statistics in a Coulomb-dominated regime. The phase ends up being changed by a multiple of 2 pi, so you see nothing. Okay, so how is this borne out in experiments? I just want to show you some early experiments that really influenced our thinking about what was the problem and what we needed to do. So Charlie Marcus, a collaborator of mine, had done some experiments where he made small devices with a top gate and big devices with a top gate. What do I mean by small? The effective area of the small device is 2 microns squared. The big device is 18 microns squared. And this is a long time ago. This is back in 2009. And in the small device, even with this surface gate, the surface gate is there to, in principle, screen out some of these strong interactions between the bulk and the edge. He saw Coulomb-dominated behavior. Now, it's very nice. There's very nice conductance plots. It's very strong and clearly seen. But it's not going to get us to the physics that we're interested in. Now, the important point here is he made a much bigger device that's 18 microns squared. And what do we do by making the device big? Well, we reduce the bulk edge interaction. We reduce the this capacitive coupling, if you will. And that, in effect, allowed him to operate this device and see what we would call AB type oscillations. In this lower panel, you see the lines with constant phase having negative slope. The problem was, if you actually look at the field scale, it's at very low magnetic field, half a Tesla. And this corresponds to nu equals 20, deep in the integer regime. As you try to crank up the field, the visibility of the oscillations is washed out, and you can't see anything. And the problem is that this is a function of coherence. It's a big device. The electrons have to propagate around this full interferometer, and as you crank up the magnetic field to get to the fractional regime, this visibility is lost. So while they have low bulk edge coupling in this big device, they don't have great coherence because it's so large. And so the idea is, what we have to figure out is how to make a really small device so it's highly coherent, but get rid of all these bulk edge interactions if we can, or at least minimize them. I see I'm already at the edge of my time, so I haven't gotten to it. But here was the fun part for us, and where you see the interplay of device physics and heterostructure design. So what we learned from Charlie and others' experiments is you put this metallic gate on top, and it helps screen out these strong interactions. One of the problems is that the metallic gate is kind of far away, so its ability to screen is minimal, and it doesn't give you enough screening to actually make the device small enough so that you can get a highly coherent device. So our trick here, or advantage, is nothing really fancy, is we said, okay, Charlie built a capacitor, but it's kind of a big capacitor in the separation. We have this MBE machine. Why don't we make a capacitor where we put the metallic gates inside the heterostructure and really close to the primary electron gas that we're interested in? So we built this structure. It's complicated on the left, but the basic idea is these little blue regions. The central one, the 30 nanometer one, is the primary two-dimensional electron gas. We want to probe the physics and transport in that device. And about 25 nanometers away on either side, we build in these high-density two-dimensional electron gases. You see the relative densities. The density in the central region is only 1 × 10^11. It's approximately at least close to a factor of 2 higher on either side, which means there's a very mobile metal sitting 25 nanometers away from the one we want to probe. And this allows us to really screen out these strong bulk edge coupling and make small devices in which this effect, or negative effect of having bulk edge coupling, is minimized. And this was just a trick of growing the capacitor in situ, if you will. This does introduce complications in the device that I'll have to show you how we mitigate right now. The one thing that's being obvious, you're saying, well, what the heck? You have a triple layer of electron gases, and the electron gases in the screening wells is actually higher density and therefore should dominate the physics over the one you actually want to look at. So how are you going to measure anything? So that means we have to build a special device. But again, we built on the observations and innovations of others in the field from the past who've used a technique for other purposes, but we just wholesale adopted it for our purposes. And so what we do is we have 3 wells in parallel, and they're 25 nanometers apart, so we can't independently contact them. But what we can do is put gates around the contacts so that we selectively pinch off the regions we don't want to have transport through. So we need to eliminate parallel conduction through the screening wells. That would be a problem. In order to do this, we adopted a technique that Jim Eisenstein had pioneered and used to great effect for bilayer systems. Completely different physics at the time, but he put gates around the omics to disconnect this, well, is selectively coupled to one or the other, electron gases he was interested in, but we use it to selectively depopulate the screening well. So if I apply a gate voltage to the top one, I can deplete the screening well. That cuts off the contact. And if I apply a gate voltage to the backside, I can also cut off the bottom contact. In that way, transport from the ohmics only occurs through the bulk, the middle quantum well. Now, there's a cartoon on the left. Of course, this makes the device pretty darn complicated. There's many, many gates, including the interferometer gates. And we don't really want to cut off, so we're not really cutting off the screening wells. We're just cutting off their connection to the ohmic contacts. So we do that selectively with these little rails of gates that are going around the contacts. But the idea is we've been able to look at transport just through the middle layer while still having these close proximity, high density electron gases to screen out the bulk edge interaction in the tiny interferometer that only exists at the very center of the device. So there's this macroscopic object, or mesoscopic is a mesa, but in the center is where the interferometer lives, and it's really small. So the presence of these screening wells around the interferometer allows us to observe AB oscillations in a really small device, 0.7 micron square area. You would think, wow, that would have a huge charging energy because of the screening wells. It doesn't. And of course, it's more coherent just because the path length is shorter. There's other fine details that we could talk about, but the way these devices work, it turns out that the screening wells actually have promote steeper confining potential. That's really good for optimizing edge state velocity, as the experts in the field will know. It's a detail that we don't have to go into now, but there's lots of benefits to designing the heterostructures this way. The one for our primary one is that we are able to make really small devices that are highly coherent, yet are not hampered by this strong bulk edge interaction. So how do we characterize that? Well, as I said, this thing is called an interferometer, but it's also a quantum dot. If we pinch off these QPCs so that the source and drain are actually in the tunneling regime, the devices in the tunneling regime, I'm looking at a quantum dot. I have to pop electrons in and off of the quantum dot, and that happens in discrete units. So if I look at a device without screening wells, build the same same device, but use a different heterostructure. For the experts, you see something here that's called a Coulomb diamond. It's where we're doing differential conductance, putting measurements of finite source drain bias across the device. And these dark regions are the regions where we're not allowed to pop electrons on because we don't have enough energy. This is a way of characterizing essentially the energy scale for charging the device. And that's given by E squared over 2C, where C defines the capacitance of the system. That's about 200 micro EV. Now, I take the exact same device, but slap it on top of one of these screening well samples, and then characterize the charging energy it's greatly diminished. It's about 17 micro EV. So, we've dramatically reduced the charging effects as measured by the height of the Coulomb blockade diamonds. Again, it's just a way of saying the charging energy has been dramatically reduced. Okay, so what does that allow us? Well, let's look at the integer quantum Hall regime. And here we see Aharonov-Bohm interference at nu equals 1. We filled the lowest Landau level completely. The magnetic field scale, as you can see, is relatively high. It's about 4.5 Tesla. And these are really large amplitude oscillations. If you look at the scale from peak to valley, it's kiloohms. Anybody can measure this. And so it's really cool because there's no ambiguity. It's easy to measure. And it's just because the device is smaller. That's the only reason. But you see AB oscillations of a device that's 20 times smaller than was possible without the screening wells. And again, this really large amplitude and robust, it survives to hundreds of millikelvin, where in previous experiments, the phase coherence as measured by damping of the oscillations is killed with changes of temperature of tens of millikelvin. So it has a lot of benefits. So let's quickly jump to 1/3, the point of this whole exercise. Now we increase the magnetic field. Now we're up at 13 Tesla rather than 5 Tesla. But again, we see the same phenomenology. We see that we have lines of constant phase with negative slope, okay, which indicates Aharonov-Bohm interference. The periodicities are completely scaled from the integer regime, where we think we're interfering just electrons. It's scaled by a factor of 3, essentially. The implication being, again, I don't want to go into all the details how you extract it, that the interfering quasiparticles, the guys that are circulating around the edge, are fractionally charged at 1/3 of the bare electron charge. So this was nice and it was interesting. And we posted this back in 2019. But if you're being kind of cynical, you'd say, but yeah, you talked about anyons. Where's the evidence of anyons? And there is no evidence of anionic phase in this data. It was actually, in some ways, you're looking at a disappointment. We don't see, we see just the bare Aharonov-Bohm interference, which tells us about charge and bulk edge coupling, but doesn't give us access to the statistical phase. And there was a puzzle, but this, of course, was solved by guys much smarter than I am, Bert Rosenau and Adi Stern, in a theoretical work from 2020. And what they actually realized is there's a competition between, I know I'm running over.
Well, if you can wrap it up in the next 2-3 minutes, it would be great. I know you're getting right to the point.
I'm getting right to the point.
Okay.
And it's because I've been rambling on, I'm sorry. Basically, there's an energy cost associated with whether you create a quasiparticle or there's electrostatic energy to keep the filling factor fixed. Okay. So there is a gap in the spectrum to create a quasiparticle, and that would be this change in the quasiparticle number within the interior of the interferometer, and that would cause the phase slips we were looking for. But because we've damped out the electrostatic cost of adding charge to the system actually minimizes energy around the central region of filling factor, and it keeps the filling factor fixed, which means no quasiparticles are created. And so there's this transition associated with this competition of energy, but it fully explains what we saw in the first experiment. We overdid it. We made the ability to screen out interactions too good. If you want, you can think of the chemical potential being stuck in the middle of the gap around the center of the plateau, and only when you go out to the extreme edges do you start creating quasiparticles. And again, I'll keep moving. So this explains our original observation, but it also tells us what we need to do in order to see the effects we're after. And there's details here that I'll skip over right now, but it all numerically and the numerics and experiments agree. So, well, they told us just what to do. We have to, reduce this quenching of the screening a little bit, and it would help to look at lower density in a smaller device. Okay, so we reduced the electron density and made the device substantially smaller, and this allows us to observe the interference over a broad range of magnetic field. So there's a new heterostructure, but the same basic idea. And so here's what the interference looks like in this device. Okay, remember I said earlier that in the fractional regime, the interference phase is both the AB phase, scaled by the effective charge, plus a term that is proportional to the number of localized quasiparticles. And if those quasiparticles change that number, you should see discrete phase slips. And that's really what you see right here. If I draw some lines, you'll see there's points where we see this AB evolution and all of a sudden discrete steps in the phase. And if you look at those discrete steps, I don't have time to explain how we fit this, but there's many ways of extracting this. You see that the phase factor, delta theta over 2 pi, that you get is pretty darn close to being 0.33. So if you actually take the average and look at these, what you get is delta theta is -2 pi, experimentally extracted 0.13 plus or minus 0.04. And that's pretty darn close to the theoretical prediction made 40 years ago that the anionic phase should be 2 pi over 3. And so this we took as confirmation that we're actually sensitive now to the anionic phase, and these discrete phase slips are associated with the change in quasiparticle number, and for the first time give us direct access to the anionic phase. I don't have time. Again, this is just to try to build up the experimental claim. We can do this again and again. We get the same answer. It comes out to 2 pi over 3, so it's reproducible. We can change parameters and we still get the same thing. I will skip this part. This is a really fine detail that's not necessary. Again, this is also details. But there are other experimental results that are completely consistent with this model of what's going on in these interferometers. And so far, we haven't found anything that contradicts that experimentally. So there's a fair amount of confirmation and new results that are coming out that substantiate the original claim. So I'll just jump to the conclusions. I know I took way too long before I got to the interesting stuff, I'm sorry, but using this new design of device and heterostructure, we're able to dramatically suppress the bulk edge coupling in Fabry-Perot interferometers. That really allows us to get at some new physics. We've measured Aharonov-Bohm interference. That was the original experiment. In the fractional regime, that was a novelty at the time. And further developments have allowed us to directly measure the Anyonic braiding statistics. And as far as we can tell, this is consistent with the model of the fractional column Hall effect that was developed a long time ago, which is reassuring. So thank you very much for your attention. I know I went over, and I will try to answer any questions.
Oh, thank you for a very clear talk and really exciting, interesting results. So if you also enjoyed the talk, please write something if you're in the Zoom session into the Zoom chat. If you're watching on YouTube, please write something in the YouTube chat about how much you enjoyed it. I'll be able to share the chat transcript with Professor Manfra at the end, so he can see all of your well wishes.
But I'd love to hear your questions and criticisms as well.
Yeah.
So give it to me.
We've already got a couple of questions lined up. So the first question is going to come from Professor Michael Hilke. Could you please unmute yourself and ask your question?
Hi, Mike. Thanks a lot for this beautiful talk, and especially also these samples, which are kind of really neat, the screening samples. So I would like to ask kind of a combined one very technical question, another one which is more general. So why do you use 25 nanometers for the screening distance? Is that sort of does it have? Yeah.
No, that hasn't been completely optimized. So we were certainly making it close so that we can estimate what the capacitance would be, right, at this level. And we kind of had a sense from earlier experiments how much we have to change the effective charging energy. So we can make rough estimates of what the capacitance would be, and therefore what the change in the charging energy would be if we had metallic layers at a certain distance. So we kind of did that empirically and guessed. Whether it's optimal or not is not clear. Now, I'll reply with a very technical response as well. We have to be far enough away that, the magnetic length here is about 9 nanometers, right? And so we want to screen the long range part of the interaction, but we don't obviously want to kill the short range part of the Coulomb interaction that generates the fractional state in the first place. So we have to be far enough away, which is several magnetic lengths, so that we screen the long wavelength Coulomb interaction, but don't kill the short range interaction that would give us the state of interest. So if we go to different states, different fillings with different densities, that separation will need necessarily to be modified in order to maintain that balance, right? Especially if the logical extension is, hey, why don't you do this at 5/2? Well, it becomes more complicated, and balancing these things becomes an issue. But that's the reason we chose at least 25 nanometer separation.
Okay, thanks. I'll probably thanks, Mike, for that.
Mm-hmm. Yeah, thank you, Mike. Could you please move your camera down a little bit, or move your head up a little?
Oh, sorry. Yeah, I can't see myself, so I don't. I should.
No problem. You're perfect right now.
Okay.
So next question comes from Professor Aharonov-Bohm. Kartik, could you please ask your question? Unmute yourself. Oh, sorry, I forgot the security setting. Kartik, I'm sorry, you weren't able to unmute yourself, but now you can. Could you please unmute yourself?
Oh yeah, thanks. Yeah, so thanks for the nice talk. I was, can you maybe go back a few slides where you showed your, yeah, this one here. It seems like there's a kind of a systematic drift of the slope as well from when I go from 8.8 Tesla to 9.1 Tesla. Do we understand what that is?
No, well, there isn't in the central region. There is a very clear change in slope as we move towards the, okay, yes, we do understand it. It's associated with this transition, which I didn't explain, and I apologize. In the central region, the theory is that you are keeping the filling factor relatively constant. Okay, so you're not adding quasiparticles. You have a few discrete events, but you're not, you're keeping the filling factor constant. As you charge up the system, of course, that still costs energy. And at some point, and therefore the periodicity, sorry, to get back to your question, the periodicity in the central region will be 3 phi naught because it's scaled. You're only seeing the AB contribution, and that's scaled by the effective charge. And so there is the 3 phi naught periodicity. Now, eventually, as you move off the center of the plateau and you accumulate more and more charge in the central region to keep the, well, to keep the filling factor fixed, there's at some point the energy balance is such that the system wants to start creating quasiparticles. And then there'll be a change in periodicity from 3 phi naught to phi naught, because each new quasiparticle that comes in it is associated with a periodicity of phi naught. So the flattening out that you see in the extreme ends is exactly what you expect if this theory actually works. So that part is consistent. So there will be a change in slope. And we can, it's a detail. If you look at the theory of Rosenauer and Stern, this is exactly what you should see. If you want to see something cool that I didn't have time for, we made even smaller devices. So this is a real detail, but this is a completely different device. Now where the charging energy is larger, but I'm in the central region where it's the AB oscillations. You see a clear transition to these flat lines where there looks like there's a little beating or modulation, and those are fine. That's the transition to phi naught periodicity. So the system changes periodicity from 3 phi naught to phi naught when it starts introducing quasiparticles, and it's really cool. You can actually see the phi naught modulation in these new smaller devices. You take that and then raise the temperature, and it starts looking like our old data in the larger device, where basically what's called, there's a thermal smearing, just call it thermal smearing. So if you want to talk about that, I can do that in detail, but we do understand it's match a simulation.
Okay.
Yep.
Yeah, okay, thank you.
Yep, thanks.
Okay, thank you very much. We have another question from Paranjati Manu. Could you please unmute yourself and ask your question?
Hello. Yeah.
Yeah.
So my question is, you seem to be able to manipulate the anyons. How far can you go? Can you go into sort of the topological quantum computing?
I'm not laughing at you. I'm laughing at myself and my field. Yeah, that's kind of the goal. Whether it's gonna happen or not, or I don't want to speculate. I'm working in this area, but I'm not going to claim anything. I think it's challenging. Okay, so what I should say to you right now, the state we're looking at is nu equals 1/3, and these are abelian anyons. Okay, so they're interesting that there's the first example of particles with fractional statistics and all that we're able to manipulate. But even in principle, you couldn't build a topological qubit with this system. You have to go to a more exotic, non-abelian state, like in the quantum Hall system, at least like 5 halves or 12/5, that we see in very specially prepared samples that are quite different from this, and under very special circumstances. Whether we'll be able to reproduce this at those states, I do not know. And I'm not going to say, oh yeah, it's, it's 6 months away. It could be never. There's just a lot of complicated physics, and the effects of disorder are much more important, and the edge states are very different. And so that's, of course, what we're working towards. I just don't know whether it's really, we're going to be able to realize it in the lab. I would like to, and of course there are many other approaches to generating non-abelian states. We're working on some of those as part of my work with Microsoft, completely different approach. But all of these have challenges that need to be overcome, substantial physical challenges.
Thank you very much. Very nice talk. Yes.
Thank you. So we're a little over time, so I'm going to just remind everyone who is not a tenured or tenure track faculty member that they're welcome to stay in the Zoom session for the après colloque, and they can get to talk to Professor Manfra a little bit more. So thanks to all who have joined us. That concludes this edition of the Physical Society Colloquium. Please come back next week for the last colloquium of the academic year, which will be given by Luciano Rezzola from Goethe University, Frankfurt. The talk is entitled Binary Neutron Stars, Einstein's Richest Laboratory. And I'm sorry I didn't say it again, but if you haven't already done so, please thank Professor Manfra in the Zoom chat or in the YouTube chat once again. So for a very clear and very, very interesting talk. So
thanks everyone. Thanks for tolerating my rambling on. So I appreciate the opportunity to speak to you.